Hello and welcome back. Since in the last video we talked about the fall time of a capacitor and how a capacitor discharges over time, we used the metaphor of Morse code. And in that metaphor, we had a light as if we had two ships communicating with each other over some sort of a light system. But with Morse code, we're used to hearing it tapped out as dots or dashes, or audibly with the speaker. So when you're trying to understand a phenomenon like the decay of voltage across a capacitor, you want to liken it to real-world types of situations. In the last video, we did that with the light, where you can have this correlation of seeing the capacitor discharge, seeing the capacitor's voltage decrease, and in this one, you'll be able to hear the voltage decrease. So we have a piezo buzzer, and the piezo buzzer gets louder as the voltage increases, and as the voltage decreases, then it gets quieter and quieter. So this is a way in which we can then hear the capacitor discharging. And starting out, we do not have a capacitor. So if I hit the button, then I get short, crisp, clear dots and dashes. And if I hold the button, and then I let go of the button, it immediately stops. All right, so we've got our three different capacitors here. We'll start out with the smallest one, and that is a 10 microfarad capacitor. And so I will put this in, and first what we'll do is we'll charge up the capacitor and listen to it discharge. So it's charged up, and then I let it go. Now that's very hard to distinguish. If we put the trace of the voltage across an oscilloscope, we would see that the voltage falls very rapidly. And so it happens so close, so fast, that our eyes and our ears cannot really tell the difference. And if we wanted to then tap out some Morse code, even though there's a small amount of capacitance, it would be relatively clear. And so there's really no problem. There's a little bit of capacitance, but one that's not really interfering with our perception of the voltage fall off. Now let's take a larger capacitor, and this is the capacitor which is 100 microfarads. We'll put a 100 microfarad capacitor in parallel with the voltage source and with the piezo buzzer and the LED. Now I'm going to hold the button and release it, and then you can listen to the voltage decrease as the capacitor discharges. So you can hear it as a short amount of time. And you might be able to estimate the amount of time that it takes for the capacitor to discharge, and in that way get some sort of a sense of the magnitude of the time constant. But when we put this into action, again, if we were trying to tap out Morse code, let's see how the message sounds when we do that. It'd be very difficult to distinguish. Certainly you're hearing the button push and you're seeing my finger, but if all you had was the audio to work with, it would be difficult to distinguish that in Morse code. So what's your only option? Well, that would be to transmit slower, have the dots and dashes be longer duration. So for example, you could and it would be more distinguishable there, but what you can see is the rate of transmission of characters is much smaller. And so if you, 150 years ago, had a telegraphy business and you spent all of the cost and effort to string a telegraphy line 1,000 miles, you would want to recoup your investment. And so by doing that, you would want to send as many messages as possible in a given period of time because you were charging for the messages and the length of each message. And if you had a situation such that there was capacitance in parallel on the line, or more realistically, an inductance in series of the line, then that would be a real problem because you couldn't use your telegraphy line as efficiently, and you couldn't transmit as many characters. As a matter of fact, the transatlantic cable, when they ran it, I believe it was the case that they could only send a few characters per minute. So you can imagine the cost of running a transatlantic cable, and if you were only able to send a few characters per minute, that would be a very difficult way to recoup the cost of the cost of laying a transatlantic cable. Well, when Oliver Heaviside came along, they were able to increase that quite a bit. So, and if I try to tap it out quickly, kind of distinguishable, but when we tap out the dots and dashes relatively quickly, then it's difficult to distinguish, and it would cause us to have a low character transmission rate in order to be reliable. So finally, we'll go with our largest capacitor, and this is a 470 ohm capacitor. We'll put the 470 ohm capacitor in parallel with the voltage source and in parallel with the piezo buzzer. And now when we tap things out, first we'll charge up the capacitor and listen to the decay. And that's a relatively long decay time. And the decay time, remember, is related to the time constant of the circuit. The time constant is given by the product of resistance times capacitance. So as the capacitance increases, the time to decay also increases. Well, let me try to type out my standard message here. And if you did not hear the click of the button and were only listening to the speaker, it'd be very difficult to distinguish that. So how slowly would I have to go in order to transmit this message in an intelligible fashion? Well, even so, going so slowly, it's difficult to determine. And so this is just an illustration. And remember that before we were seeing the voltage through an LED, and today we are hearing the voltage decay across a piezo buzzer. Now in your lab, you will be having a square wave, a oscillating function generator that will just be turning on and turning off. And the faster or slower that you turn it on and off, it's very akin and analogous to the pushing of this button. And when we have a high in our function generator's voltage source, and then it suddenly goes off, you can get a sense that it'll be slowly decaying, and that's what you'll be investigating in your lab this week.